Most groups are surprised when I tell them not to include detergent in their blocking buffer. And that's because it's really become common practice to include a detergent in the blocking buffer solution, even though it wasn't included in the original protocol from the 70s. When you add detergent in your blocking buffer, the detergent will interfere with the binding of the blocking buffer proteins to the membrane. And this is exactly what we don't want to happen. So for effective blocking, we want the proteins from the blocking buffer to bind to the membrane uninhibited. We want them to occupy all the open spaces on that membrane. Also, some detergents, such as Tween 20, will autofluoresce, and that's going to lead to an increase in background. When using milk or BSA as your blocking buffer, make sure to prepare it fresh the day that you need it. Stir the blocking solution for at least 20 minutes to avoid particulates that could cause speckling on your membrane. Also, you don't want to filter your homemade blocking buffer. Filtering can reduce the protein concentration because the proteins will be retained by the filter paper. This would lead to a reduction in the blocking efficiency. If using commercially available blocking buffer solutions, you want to make sure to use them at 100% strength and not dilute them. Typically, membranes are blocked for 1 hour at room temperature with agitation. You want to be consistent with how long you block your membrane for. Using an excessive concentration of blocker or prolonging the blocking step may mask your antibody-antigen interactions. For this reason, overnight blocking should also be avoided. After you have blocked your membrane, do not allow the membrane to dry until after your final wash. Drying your membrane at any step after which it has been blocked will permanently adhere whatever's on the membrane to the membrane. So this means that you can no longer remove your primary or secondary antibodies from the membrane. Many researchers use PBS and TBS as dilution buffers for their blocking agents, and they often consider them to be interchangeable. However, in reality, they really aren't. So it's important to note that not all blocking buffer formulations are suitable for every experiment. There are some instances where PBS just can't be used. So in some cases, the primary antibody will bind to the phosphate ions in the PBS buffer, and that's going to prevent your primary antibody from binding to your phosphorylated target. So in these cases, a TBS-based blocking buffer is the better choice for detecting your phosphorylated proteins. Now for non-phosphorylated targets, it's really best to test the blocking buffer in both PBS and TBS to see the comparison. So once you've determined the best type of buffer, you want to make sure that you use that same buffer for your entire Western blot protocol. It's important to test out multiple blocking buffers to determine the best one to use for your targets, as you're likely to see considerable variability in your signal intensity and background noise. When choosing your blocking buffer, keep in mind that BSA is not as efficient blocking buffer for NIR Western blots, while milk offers a cost-effective alternative when you're not probing for phosphorylated proteins. For the most consistent blocking buffer formulation, you're going to want to use a commercially available blocking buffer. Remember that these blocking buffers are available in both a protein-based and a protein-free formulation. Now that we have learned about the best practices for blocking the membrane, it's time to carry out the protocol and prepare to move on to the primary antibody incubation step. In the next lesson, we will watch Sally in the lab as she shows us how to block the membrane.